Okay, well, thanks everyone. I'm the last presentation before lunch today, and the title of this is Using AI in Production, Photogrammetry, and Geospatial Workflows. Okay? All right, so when we say, everyone familiar with the term production? You know, I kind of want to make sure. Okay. All right, so when I'm referring to production deliverables, because we're a software company, for us production is, the true ortho photos we create, the 3D point clouds and classified 3D point clouds, volumetric measurement, etc. So these are, these are capabilities that we deliver to the user, in the software, like that. Production deliverables, true ortho photos, classified 3D point clouds, and volumetric measurement. So I want to talk about those deliverables, what goes wrong in production. So, I mean, who here is involved in creating production geospatial data? Probably a fair amount of people. All right. Has anything ever gone wrong?
Never.
Never. All right. Okay. So, yes, I mean, things go wrong, and our goal, of course, is to, when things go wrong, to have methods available for the user to correct that, to identify it and correct it. Then, after we talk about what goes wrong in production, my focus will be on how we've been implementing some AI methods to improve this automation and some of those automation methodologies and then results. Okay. So I just mentioned what is production. So that's what our users do with the software. They might be involved in creating topographic maps, orthomosaics, 2D and 3D vectorization, etc. Now, kind of what inspired this presentation? Well, let's see if this runs. So, at the beginning of this year, we released a new module within our software specifically for volumetrics. Okay, and because we had identified that people use our product often for doing volumetric measurement, and we thought, okay, if they're doing volumetric measurement a lot with our product, how can we make it more streamlined, automatic, efficient, right? So one thing we kind of settled on is that people, instead of clicking around the boundary of a stockpile, for example, all the vertices around it, people just want to click on one, click on the stockpile and just get a volume measurement, right? And so that was sort of the genesis of us getting into this space of like how can we help the user generate data deliverables as efficiently, as accurately, as efficiently, and as automatically as possible. So we implemented, we call this Stockpile Studio, so we implemented this version that you saw, which is where people just click on the stockpile, automatically gives them the measurement. Well, then they said, hey, that's too much work. We don't even want to click, okay? We just want you to find everything automatically. Just give us one dial and find everything, okay? So that's what we added next was in Stockpile Studio was they can come here, fewer or more, and it finds all the stockpiles, measures their volumes automatically. So that's kind of the battle we're up against, right? I mean, it's a challenge from our perspective because it's fun to envision ways to automate the problem for the user, but it also removes so much expertise, so much knowledge, right? Like, well, how do we do it, right? I feel like it's this battle of we're trying to make things better for the user, but at the same time they're losing sight of like all the intricacies involved with the solution. So it's like, well, we need revenue to pay ourselves, but at the same time, we want the user to be aware of like, hey, what's actually happening here. So anyways, that was the genesis of today's presentation, was like, okay, how, for stockpiles, for volumetric measurement, we automated that as much as possible. but how can we do that in other areas or other aspects of geospatial production? So the first thing I wanted to go over was true orthophotos. So what goes wrong with orthophotos in production? So before I even go through slides, for all those production people doing production work out there, have you ever seen any issues in an orthophoto before?
Not one ever. We hate bridges.
Quality of the positioning data of your photos, as an example.
Quality of positioning data. Bridges.
We hate bridges.
Yes. Anyone else?
Walkout basements.
What's that?
Walkout basements.
Walkout basements. Yeah.
Building lane in general.
Absolutely. Okay. So let's see. I'm dealing with people who understand the problem, right? A lot of people, there's like, well, why did this happen, right? So for production orthophotos, what we usually see from bad data, what we usually see happen where we have to repair something is, number one, you just have bad data. Number two, you've got good data, but it might be too coarse, right? And then the third option is you've got missing data. So if you've got all these things, it shows up in the quality of your orthophoto, your true orthophoto. Now, if someone would have said, Ben, what's a true, orthophoto versus a true orthophoto? I always assumed that an orthophoto was a true orthophoto, right? It incorporated the surface model, but historically, orthophotos were using, for the base elevation, they were using a terrain model, right? So the building wasn't necessarily modeled, just the ground elevation was modeled, and then when you ortho-rectified it, what you'd end up with is something like this, where in the, let's see, maybe it's time to use this. So this is what you would see in the orthophoto, but the actual, if you were to actually get up on the top of the buildings, which Dean, you used to do that, is my understanding, right? Yeah. We did that at Purdue once. We had a project where I can't believe they let us do it, to be honest. They probably won't do it anymore. But we would get on these, 10-story buildings and lean on the edge to pick up the corners for an NGA project. But the point is that if you were to go out there with a GPS and actually measure the corners of the building, what you'd see is the actual corner is here. Like in the orthophoto, the corner should be here. But because of this relief displacement, and the fact that building geometry wasn't modeled, then you see the building corner being over here. Okay, so I just wanted to make that distinction because I'm gonna be talking a lot about what some of the effects and issues that happen with true orthophotos. So again, same example over here. Like this is what it would look like in the orthophoto, but this is actually where the building footprint would be. And then just kind of a dynamic example of that in action, where you can see, okay, this is not true orthophoto, and then true orthophoto, right there. Perfectly top-down perspective that incorporates the building elevation into account. Okay, so and then the second thing I wanted to mention, because this is a problem that I would say is much more unique to close range or drone imagery, right? So if you look at manned aircraft imagery, so we got Ken Scruggs, right? Ken, there he is. Okay. So if you look at one of those 230 megapixel images from Ken, those beautiful DMC images, the relief displacement at the scale he's flying at, right? He might be at 1,000 feet above ground. It's even for a relatively tall building like this, it's not as big of a deal when you compare it with like a typical flying height of a drone, right? Like we can see, there's significant relief displacement here due to that perspective camera model. And so anyways, I would say this problem, this orthophoto correction is more I would say it's more prevalent with drone imagery versus traditional aerial. I'm not going to say it's not present in traditional aerial, but it's not as probably as common. All right, so I think everyone here probably knows this by now, but yeah, for these close range drone production projects, your true orthophoto is only as good as your 3D. Okay, like for me to get these very nice building edges on this true orthophoto, that means I have to have very good 3D edges underneath it for my point cloud, right? And a good 3D DEM. So if I have bad 3D edges, right, then that's gonna propagate into my orthophoto. And you can see here that this is just the 3D mesh of that same rooftop area. You can see significant height variation here. But that's the point I want to drive home, is that your true ortho, the quality, the geometric accuracy of your true ortho is only as good as the 3D data that's underneath it. Okay? All right, and then I just threw this in here. I've got, if anyone, ortho versus true ortho. So if you're doing, if you're flying with LiDAR plus images, right? So you're saying, hey, I'm going to take the 3D from the LiDAR. It's an active system. The 3D kind of comes for free, right? The LiDAR is collecting that. Now, if you're only flying a photogrammetry project, only got a camera, right? How do we generate that 3D? It comes from our dense image matching, right? So we have to generate that from the images, and that's a whole process, really a whole science in and of itself. Now I've got one. I do have a free T-shirt here. So if anyone can tell me which one of these 3D meshes is aerial photogrammetry. So only images versus LiDAR plus images.
The one on the right is just photos.
One on the right is just photos?
Yeah.
Man, I gotta give you it. All right.
It's the trees. Look at the trees. See the tree?
Coming at you. Oh.
They'll bring you a T-shirt hazards.
Yeah, I know. I didn't have the T-shirt again. Okay. Nice eye, Victor. He's late, but he's coming on strong. All right, so here's some examples of bad data. So we kind of, we went through some of the biggest, or the projects where we identified, like, okay, let's find the worst sample and see if we can fix this orthophoto. So this is a classic example of where you start seeing issues in true orthos, right? So if we have to generate the orthophoto from the images directly, from dense image matching, you sometimes have scenarios like this, because the client, they might fly with low overlap, and they fly over a metal roof, and one of the problems, drones are great, but it kind of it aligns with like the broader theme that I brought up at the beginning. They do so much of the work for you. No one's adjusting camera settings. No one's, they're a global shutter. What's that, right? Like keeping the shutter speed the same. So what happens nowadays is you got a DJI or whatever that drone might be. It has these camera settings that it's dynamically changing those as you fly. Changes the white balance, changes exposure, etc. And so what ends up happening is you have situations like this where you fly over a metallic roof. In one frame, you got like this dark blue image, and you can kind of see dramatic differences in lighting, right? You've got the ground is darker, the building's darker, and then on the right-hand side, of course, you've got more reflection and higher exposure. And so in the software, right, the user, the sad part is they have no idea. They just, what happened? Why did my orthophoto come out like this? Right? It's your fault. It's your fault. They don't even know that this is what's actually happening. So it can be frustrating, but at the same time, it's a challenge for us as a software company. Is okay. Well, how do we solve this problem, right? And like I said, the root cause is you got different illumination, different camera settings, and so when you're doing dense image matching, if you don't have LiDAR, you're doing dense image matching. Like we're trying to match. Number one, this is a homogeneous surface, right? It's just the same color everywhere, and number two, the color itself is different. So when we're trying to do dense image matching, right, we can't get good correlation between these two images to reconstruct that roof really well. Okay, so what ends up happening is you can have bad, there's basically two types of bad data that end up happening. You have bad data inside the building envelope, so you can see a little bit of that here. I tried to highlight the building envelope in red. And then you've got bad data outside the building envelope, okay? And those are two kind of unique problems, okay? They're related to the same thing. They're ultimately related to, like I said, bad or missing data, but it manifests itself in the ortho photo. It can be either inside the building footprint or outside. Okay, so if it's inside the building envelope, right? So if it's inside, we have manual methods in the software that make correcting for that issue, it's quite easy, right? You can correct for it in 3D, so you can use like our stereo viewer to measure the outline of the building and in 3D, and then we'll use that, we'll select the image that views that, and then we'll put that into the ortho, and it works perfectly, right? Looks beautiful, it's geometrically correct, right? Because the 3D is correct, and from that, the 2D is correct as well. And again, most people, if I go back to this, I hate to say it, I really, really hate to say it, they are less interested in the geometric accuracy of the building roof than they are the aesthetic, right? So as long as it looks good, they, or if it looks bad, like that's a worse outcome than it being geometrically correct. So the point I'm trying to get at is, so when that bad data is in a roof envelope, it's relatively easy to fix in the tools that we already have. But like I said at the beginning of this presentation, it requires more than one button click, right? So naturally, people don't want to do it. All right, now if the building data is outside, or if the bad data is outside the building envelope, this is kind of a harder problem to solve, right? I mean, it's still very doable, but at what cost, right? Because then we have to, from a software perspective, it's just more steps for the user. It can easily be done. It's just, again, we're kind of running into that issue of, well, the user, they just don't want to go through that work. I hate to say it, they don't want to do it, in general. All right, so that's one example of bad ortho photo data and the reason behind it. Here's another example where you've got good 3D, but it's too coarse, right? So you've got, this is statewide LiDAR data, and it's at maybe 1 or 2 foot, 2 points per square foot. I forget what it is, but so in this case, a user, he said, hey, I want to do a combined LiDAR and photo project. So he brought in statewide LiDAR, but then he had high resolution drone imagery. So that's what he had on the right. So when we go and create a DEM from that LiDAR imagery at that density, the overall accuracy of the data is good, but what ends up happening? If you look at this building roof, right, when we created a DEM just from the LiDAR data, you've got like this effect right on the edges, just related to the point density, okay? So that, again, that manifests itself into the 2D ortho, and again, they're saying, well, hey, why aren't the building lines perfectly straight? So how do we fix that? And then the last couple issues to bring up, and I would say this is our biggest issue in, at least for us in photogrammetry software, is what we call facade bleed with true orthos. So, and it happened, it probably only happens, I don't know, 5. It's not a very common occurrence, but it certainly happens where, again, it gets back to this dense image matching problem where you have this surface and it's all the same color, right? It might be washed out, it might be just all the same pixel color. It's all white. There are a couple of windows here in this example, but you get the idea. Now, what if the roof was white, right? I'd say a more common example is you've got like a concrete roof and then you've got a concrete side. So you don't, it's hard, if it's washed out like this, it's hard to know from a dense image matching, like, okay, where does my roof stop and my facade begin? So again, the reason I'm telling you this is that it's going to be important in how we solve it. So that's the reason why I'm going into these details. Again, here's vegetation can cause an issue. So here's an example where you've got a tree that's hanging over this very near a house. And you can kind of see here, yeah, like, it just causes some issues in the true ortho. You can actually see a little bit of facade bleed. That's what we call the facade bleed. So this is a true ortho. You can just see a little bit here where, again, that washed out facade can sometimes bleed into that true ortho. Okay, so now I want to talk about working towards automation, right? And I always go back to that example. People don't want to fix things manually. They just want an automated method that works. But for us to design an automated method, we have to know what is the problem, what are the pieces to the problem, and then work on a solution. So again, our goal here is for production, because the user has to be able to, we're not in front of them, they have to be able to do this all on their own. We want a one-click fix that's repair roof, okay? So we for solving this problem, we have really four sets of data that go into solving the problem. We've got the input RGB image, right? It's up here on the left-hand side. It doesn't have a roof, it doesn't have a house in this one, but then we also need a dense depth map. We utilize surface normals, and then from these two, we also then ultimately build a semantic segmented image, right? So I'll talk about that next. Okay, so just so I know some of these terms might be a little bit, may or may not be aware of them. So a depth map, for every pixel in this RGB image, right? For every pixel, I have a distance to the 3D object in the scene. That's what a depth map is, okay? So that's what we're seeing here, right? So this is this yellow here is a further distance away, of course, than this roof facade. Okay, so for every pixel in a 2D image, the distance to the corresponding object in 3D space. Remember, the problem here is introduced where, because we're doing dense image matching, this is the problem. We don't have a dense depth map, right? Again, here's an example where you've got homogeneous white pixels. And so we're saying, hey, we need a dense depth map, but we don't have one from the multi-view stereo. So that's what we're utilizing. That's one of the pieces of this AI capability. All right, so the second thing is normals. So again, for every pixel in a 2D image, we want the orientation of the 3D scene, right? Okay? And the reason we want normals is we want to be able to distinguish between the roof and the facade. Okay? That's an important distinction we want to be able to make in the images. Okay? Because if we know that distinction, then that will help inform which pixels to select for the true ortho photo. Okay? And then the last piece of this is that we have to do semantic segmentation, right? So for every pixel in a 2D image, there's a label that goes along with that pixel. Every single pixel. So there's, buildings. Here's a car, where this is labeled as a car. Ground, trees, road, etc. Okay. And so what we did is we had to. There's a lot of open source projects. There's a lot of literature out there, and I can I see maybe I can consult with these guys, but there's not really a lot of people do different they have different classifications, right? There's not really a unified set of classes that we were able to find, at least in our research. So we had to take different data sets and then unify them with respect to the classifications, the segmentation classes we want. And this is what we settled on. So we've got, and I think we've expanded this to some degree since this, but we've got sky, ground, water, tree, person, low vegetation. So this doesn't include grass. Grass would be ground. It's more shrubs, plants, flowers, trees. We've got roofs. So we want to know the roofs. Again, remember what I said about facades. We want to be able to. We don't just want a building. We want to be able to distinguish between the roof and the facade. Okay. And then, of course, vehicles, street furniture, etc. All right, and this is just a couple examples. So, just starting out, this middle here, this is an example of what could go wrong from like dense multi-view stereo. It's kind of an egregious example, but you can see like there's missing patches here in the stereo, in the depth maps we generate from multi-view stereo. Okay. So our goal is to use monocular depth maps. From MOG is the monocular geometry estimation, MOG. We want to use those and supplement our depth maps that we generated from multi-view stereo. Okay, so basically our goal is to kind of fill in missing areas from multi-view stereo with monocular estimates of depth. Okay, monocular estimates of depth. This I group that into, this is AI, right? Like it's not a you're looking at an image and getting a depth estimate for that, but it's not based on photogrammetric principles per se. Okay. Next slide. So here is again, instead of multi-view stereo depth, here is MOG depth. Okay, so you can see here that we're not missing. There's a depth value for every pixel. Those depth values are not necessarily correct, but there's depth values. Yes, Victor.
Can you briefly touch on how it does that? I mean, it sounds like magic.
Well, it involves a lot of training, right? So we, there's truth, right? So there might be, you've got a source image and you've got a true depth image that it trains on, or thousands of depth images, right, from different data sets. So yeah, it involves training on known truth and then building the model for that. Yeah. And because that's one thing that we can leverage, just because we have being a production photogrammetry, a software company. I mean, we've got I don't know how much data, but lots of it. Both that we've collected that our partners let us leverage as well. So,
Ben, is it essentially, as it progresses in filling in the data, it's basically predictive based on?
yeah, we'll get into the details. Yeah. So now this is the semantic segmentation, right? Where we're going through and we're classifying. Hey, here, what's in the scene, right? Because we want to be able to use that information to generate better 2D and 3D data. Because if we know, hey, this is a facade, this is a roof. Yep.
How many classes do you have ordinarily in a standard run, and can you add additional classes?
Yes, we started out with these 11 classes, and I think we expanded it to 17 recently. We were trying to align ourselves actually with the LAS classification standard. I know there's a lot more, but I think
Which one?
LAS.
Oh, LAS.
Yeah,
Okay.
LAS.
Ben,
Yeah.
in that last video you had there, looking at your table,
Yep.
this is vertical straight down, I see percentages of sky. What's going on there?
Oh, let's play it again.
The very top.
Oh, I don't know. Who knows? I don't see it labeled. So this is also fairly old results. I mean, it could be Yeah, I'm not sure.
It's a good question, though.
Yeah.
It's that blue truck head.
Whoa, that's it. Makes so much sense now.
He's already poking holes, you know? I mean, all right, so let's keep going. Okay, so can we repair production data sets with these? That's our goal. All right, so here's, again, we looked through some of the most egregious examples. So here's an example of a white roof, right? It's a steel white roof. And if you actually pull the RGB images, I mean, it's all white. I mean, it's 255, right? No variation whatsoever. So what happened is, you know, this is not an ideal outcome. Well, why did it happen, right? Here, so this is the DEM from multi-view stereo. You can kind of see how white this roof is, right? And again, when you have a camera that changes white balance, illumination, like these problems are difficult to solve from a classical multi-view stereo perspective. I'm not saying it can't be solved. I defer to maybe these guys on the best way to solve them. But it's a difficult problem. I mean, no matter what. And so you can see here, this was the point cloud. We got the ridge fairly well. A few areas on the roof, but yeah. So first part is finding the roofs, right? So you can kind of see here that with the semantic segmentation, you know, that's the first thing we do is we want to be able to repair it. We want to find the roof. So you can see we did pick out the roof of the truck, but we found, you know, this is the roof of the storage building, and then here's this outline. Here is, I might have mixed up a couple figures actually now that I'm looking at it. So we find the roofs. Then we take the MOG depth. This is a simple case because it's a two planes on the roof. But we merge our MOG depth with the multi-view stereo depth, and this is the output, the combined depth. And this is the combined depth map. You can see here that, of course, these are occluded areas in the image. And then this is the final depth. And then the final ortho. So you can see here that we've dramatically, if we go back here, obviously this is a much better outcome like this, right? And of course, like I said, from a production perspective, this can't just work like maybe one time out of 5. It has to work every time, right? One click fix, okay? So let's go to a more egregious example. And this is probably this is the worst one that we're aware of that we've ever had. So this is a domed metallic aircraft hangar. And this, wow. Yeah. So if you look at the raw images, the illumination changes on this particular one you go from very dark roof to very light roof. You've got sun illumination changes, like on each, because this is down in Florida. So this is, like I said, this is about the most egregious outcome we've ever seen in production. So we want to say, hey, could we fix this problem with a one-click method, right? We can fix it with manual methods, but how can we fix it with a one-click method? Okay, how can we get to this? So again, so you've kind of seen the workflow that we have in place, which is we have to, number one, get the segmented image. We have to generate that semantic segmentation. So we need a classified image for the source. And that lets us know, hey, what is this a building? Is it a facade? Is it ground, etc. So then we excuse me, run out of voice here. So we label every photo by class, and then the unnecessary classifications are dissolved before use. So then we, again, kind of segmentation on the scene. So then we use the monocular depth model to supplement areas where our depth estimates are bad. And again, we're using the normal map as well to help understand, the boundaries, right? Where is there an edge boundary of a roof to a facade, or some sort of vertical change, right? And then a derivative of that would be tilt, right? And then here's the depth as a point cloud, but again, we're trying to get metric depth, not just depth, right? Because if it looks good, but it's not correct, it doesn't really help us out very well. Okay, so yeah, I'll kind of push forward just because we're running out of time here. So structures removed, ground filled, and then structures replaced. Okay, and here's the structure footprint and the final surface. Okay, and so again, we're trying to fit the depth map from multi-view stereo to the monocular depth map, which in this case, obviously, you've got huge problems. Long story short, we go from before to after. Again, this happens all in an automated fashion. So I'll just kind of show what that looks like. You've seen that already. So here's what it looks like in production. Okay. So that, again, getting back to that one-click fix paradigm. Oh, sorry. Any questions so far?
So I have one
Yeah.
question. So when you fill the depths from the views, which view specifically are you using?
Good question. So we typically start with the most nadir image over the object that needs to be remapped. So we start with that one, and then depending on occlusions, then that's kind of our master image, and then depending on what's left, then we fill that in with secondary images. Yep.
Do you see inconsistency issues between those?
We do.
Secondary.
Yes, yeah. So that's where it starts getting complicated. Is if you've got a really big building, right? So let's say you select the most nadir image, but it only sees part of the building, and you're trying to fix the whole thing. Then that's where it starts getting complex, right? Because now you have to do alignment of you're doing, and that's where really where monocular depth kind of breaks down. Because the reality is it's not, they say, oh, it's close, it's metric depth, but we have ground truth, and we can see that it's definitely not. It's not even close. So that's kind of the problem we're trying to solve now, is the best way to integrate multiple monocular depth estimates into this process. Yeah. Now, the last thing I wanted to bring up is, so we started this again, the genesis was, okay, we started with the one-click fix for volumes, then we wanted to get to ortho photos, but because we're generating this segmented data, can we, now since we've done all the work for that, can we just classify our 3D point cloud from the images directly? Okay, so can we get it for free, effectively? So here's an example where we've got our 3D point cloud, and we're going to run that classification pipeline. And this is kind of what it looks like in real time, so incrementally.
Ben, what are your thoughts on accuracy on what you're getting? I mean, it looks like it's doing a good job.
Yeah, great question, Colin. So, oops, I didn't mean to exit out of that. So what we've looked at is, how good is monocular depth? For planar surfaces, right? you can, there's a set of transformations, like a affine transformation, right? We can map one planar surface to another. So we can map our photogrammetric depth maps very well to the monocular depth maps in a planar surface, right? Now where it starts getting complicated is that hanger, right? You've got a domed, there are some planes in it, but you got a domed surface. You got anything that's like geometrically complex, then it starts breaking down like what you can actually do rigorous math with and what you just have to YOLO, for lack of a better term. Like ultimately it comes down to do you want geometric accuracy? Does the user want geometric accuracy, or do they want aesthetic completeness? And like I said, a lot of these tools are available to give them both. They're manual tools.
Yeah.
You just don't want to use them, sadly.
But some people like manual tools.
Some people do. We love those people. We do. So that's an example. And then once let's see. Once it's classified, one of the things we're looking to do is generate. Once you have a classified point cloud, right? Generating a bare earth surface, from that is trivial, right? You can say, hey, I just want the ground areas. I thought that was in here somewhere. Yeah.
Ben, you've been talking about dense point clouds, but even with LiDAR, choosing which point gets matched to which pixel causes the same problem. So that this workflow is point cloud, not where the point cloud came from.
Yeah, correct. Yep. So it would cut, in the LiDAR scenario, that's a more ideal scenario because it's an active sensor and we don't run into the roof issues.
Planes
right?
are true.
Yeah, exactly. So that one, the segmentation will, should work, really, really well. So anyways, this is our goal because from a production standpoint, people, they want to create point clouds, orthophotos, but at the end of the day, if they're doing topographic surveying, they want contours. They want that bare earth DEM. And so any way to classify the data and make it available to them in these distinct classes is a win from our perspective. So whether it's derived from dense image matching and photogrammetry or LiDAR, either way, it can still leverage the same workflow. Let's see. Yeah, that's about it. I think it's 11:50. So, do I have any other slides? Like does a double take. So, I guess I'll leave the remaining few minutes before lunch arrives for questions. Anyone have any?
I got to follow up to my accuracy question.
Yeah.
Understand about the more complex surfaces there. What about the accuracy of the classifications? I mean, how do you, if the late great Chuck Olson were here and saying, "Can you do better than 85%?" Would he be happy?
Yeah. Let me find maybe this example. So we say segmentation at the pixel level. Now, what I will say is that you start seeing some. Let me just go back to slideshow here. If you were to zoom in on this roof edge, right? What you'll see on the boundaries is you'll start seeing some. Because we're using the monocular depth as one of the inputs along to generate the segmentation. Right on that edge where you go from. Monocular depth doesn't do a great job on edges, so you'll see like a very high gradient right at the edge, and it's hallucinated, right? Because if you think about a roof, it goes like this, and so what you'll see in a monocular depth map right on that edge is like this bleed. So it's still a problem, like from a when you say like what level can you get, like it's very good, but there's still certain areas where it's not pixel level segmentation quality accuracy.
But the class, the actual class types, you're reasonably confident of.
Oh, yeah, I mean, I'd say it's about 90%. There's some, we see some things on like edges of projects, certain, due to illumination areas. Illumination changes, like you can see, sometimes it'll misclassify a road as being ground, for example. But we don't have any metrics like that I could say, hey, 96% quality.
It's so striking me as quite significant to be able to do that without the aid of LiDAR data. So,
I mean, and that's the whole genesis of this, though, because if we had the LiDAR data, this wouldn't be a problem,
Yeah,
right?
yeah.
Because we have good 3D.
yeah.
Yeah.
Does the semantic segmentation take into account like elevation, or is it only just RGB pixels that it's classifying?
No, so it's leveraging, it uses RGB, and then it's also using the monocular depth and then the normals, right, to feed in. Because if you were to just do like a vanilla semantic segmentation, like this would be classified as a building, but you wouldn't know, for example, a facade versus a roof, right? It would just classify it all as a building. And so that's what's different about us, is that we want to be able to distinguish between those things. And so that those inputs feed into the segmentation. Any other questions? Yes.
Are all of your semantic photos you're using just nadir, or are you guys pulling in oblique as well?
So it's not limited to nadir or oblique. I'd say that oblique, generally speaking, we get better 3D results with, because you can see the facade, right? It's not like just a little sliver of pixels on the edge of a roof. So it's very flexible. It's just not as much. This isn't as much of a problem with oblique data.
Right.
Yeah.
Okay.
Any other questions? All right. Well, thank you all. Appreciate it. Yeah, if you have any questions, feel free to email myself or Emily. And I think it's lunchtime now, so we're just waiting for lunch to get here. It's en route.